I'm Walter Bright, and this is Destroy All Memory Corruption. Memory corruption is a pernicious and expensive problem. Systems programming languages generally have traded off power for susceptibility to memory corruption. It is impractical to manually review code for it. Much experience shows one can never be sure code is free of it, and even if it is free of it, the next change to the code can introduce it again. Of course, the worst of these memory corruption problems are buffer overflows. Fortunately, D has had buffer overflow protection designed in from the start. In particular, it encourages dynamic arrays rather than raw pointers, as dynamic arrays can do runtime array bounds checking. The use of ref arguments helps as well by not allowing arithmetic on the pointer. Constant immutable help by not allowing writing through pointers, reducing the surface area of problems. Next, DN stack corruption, loosely defined as using pointers into expired stack frames. Mechanisms for detecting and disallowing such rogue pointers are parameter attributes such as ref, return, and scope. Aliasing problems come about from casting things like integers to pointers and using unions to cause pointers and non-pointers to share the same memory location. These are disallowed in @safe code. Ending corruption from storage allocation problems is accomplished by using the garbage collector. I know what you're thinking. You don't want to use the GC. Yes, I understand. A GC is not normally the weapon of choice with a systems programming language. It doesn't offer the fine control desired. Typical memory allocation strategies are one or a combination of the following techniques: explicit malloc free, writing a custom allocator and deallocator, using RAII with destructors, and using reference counting. Taking a look at malloc free, the memory corruption problems characteristic of it are mallocing memory without freeing it, also known as a memory leak, freeing a pointer and then continuing to use it, also known as dangling pointers, freeing memory more than once, no special name for that I know of, and finally, freeing memory that was never allocated in the first place. RAII, short for Resource Acquisition is Initialization, is a great fit for objects that have a scope lifetime, but it's an awkward fit for other patterns of allocation. Then there's reference counting, and I should point out that reference counting is often built on top of RAII. This code is an example of a reference counted object. I omitted the reference counting machinery from the object because that's not germane to the point here. What I wanted to focus on is where things can go wrong with reference counting. Our reference counted type S has a single field for the payload, P. The main function allocates an object S and initializes the payload to point to variable I. Then the function fun is called and a reference to S is passed to it twice. In function fun, S is reassigned, which by reference counting semantics frees the old value and assigns a new one. But the other reference to it is still active, but its P is never initialized. Assigning through that P results in memory corruption. Stripping all of the boilerplate away here makes it obvious what is going wrong, but real-world cases can be very hard to spot. The actual problem here is we have two pointers to the same object, one or both of which is mutable. And the problem stems from one of them pulling the rug out from the other one. This specific problem was addressed by DIP 1021, argument ownership and function calls, which disallowed more than one reference to the same memory object being passed to a function's parameters, if any of them are mutable. But it's limited by only being able to check the obvious cases and, of course, only working for functions. Let's generalize this further beyond just functions and disallow more than one reference to the same memory object if any of those references are mutable. You might recognize this as a foundational rule that Rust adheres to. Phrasing this in a slightly different way, if you have one mutable reference and that's it, obviously this works. And if you have many const references, it also works because none of those const references can change anything. So those two cases are allowed. What is not allowed is if you have more than one mutable reference or if you have mixed mutable and const references. Now, I have convinced myself that this works, and I don't know really how to prove it, but other people have proved it, and I'm confident that this works. Think about it, and I think you'll agree. That single mutable reference to a memory object is said to own the object, i.e. it is the owner. And the most straightforward way to create an owner is to have a function which returns a unique pointer and assign that to a variable. And now that variable p owns the memory object returned by the function f. Ownership can be moved, also known as transferred, from one mutable pointer to another by assignment. Note that I did not say copy, I said move, and having it move has implications. Here the value of function f is assigned to p, making p the owner. We've gone over that before. Then assigning p to q now makes q the owner. The key thing that happened here is now p becomes invalid. This is what I mean by it is moved to q. It is not copied. This is very important. The next line assigns through q, which is fine because q is the owner. The next line assigns through p, but is rejected because the value of p is invalid. It was made invalid because its ownership was moved to q. I'll wait for a second to let that sink in. This is an extremely important point. It is possible to copy rather than move a reference, and this process is called borrowing a reference. Assignment is also used to indicate copying and is distinguished from moving by the scope annotation on the left-hand side of the assignment. In the example, B is borrowing from P because B is a scope pointer. We can assign through B to set the value it's pointing to. Then we assign again through P and assign again through B. But wait, what? Why is that assignment invalid, but the one through P was valid? It's because the use of P invalidates any borrows. We need to have a rule for when a borrowed reference ends, and it ends when one of the following holds. The last use of the borrowed reference, i.e. it isn't used anymore. The borrowed reference goes out of scope, or the owner is used again, and as we saw in the previous example, when the owner is used again, it invalidates all the borrowed references. The first of these that occurs ends the borrowed reference. The lifetime of a borrow is defined as the point at which the value is moved or copied into the borrow until one of those three conditions happens. This is determined using insert scary music, data flow analysis, and I'm going to show you how that works in one slide. First, decompose a function statements into a collection of blocks of expressions connected by edges that represent the control flow. If statements, loop statements, switch statements, and especially the goto statement all transform to blocks and represent control flow edges. Second, construct a data flow equation for each block in the form Output equals the transformation of the input. The input is the state of the variables at the beginning of the block, and the output is the state at the end. The transformation are things like which pointers get read from and which are written to. Next, solve the n equations for n unknowns, the unknowns being the inputs and the outputs. This is done iteratively until it converges, which usually only takes a couple of iterations. How about that? 5 years of Caltech in 5 minutes. Just think what you'll know after 40 slides. I'm going to bring up another term here using the same example. When we have a function which returns a pointer and we assign that to p, we can call that pointer creation. And the point of this new term is if a pointer can be created, then it can be destroyed. Destroying a pointer happens when it gives up its ownership by transferring its value to another pointer, as mentioned previously, or by passing it away to a function. If we didn't destroy the pointer and the function ended, we have an error. And the error is that p is live on exit, or also known as a dangling pointer. And this is an error in live functions. Here's another example of this in action. The function h is taking ownership of its parameter p and disposes of p by moving it to function g. P is then g's problem, but g doesn't do anything with p. P is live on exit, and the classic dangling pointer is diagnosed. Functions can also borrow pointers by annotating parameters with the scope attribute. The function m borrows pointer b and does nothing with it, which is okay. Function n borrows pointer b and loans it to function m, which is also okay. But then it attempts to make b an owner by passing it to function g, which only accepts owners, which is illegal. All examples so far have been a linear progression of code, one expression following another. But real code has control flow. How do at-live functions deal with multiple control paths? This is the job of data flow analysis. In the example, there are 3 blocks of code in blue circles, connected by 3 arrows representing control flow. Not shown are the statements that cause the forking of control flow, but presume they are some sort of if-then statement. After p is initialized as an owner by being assigned a value from function f, control forks. The then branch goes on to transfer p's value to function g. The value of p then becomes invalid. The 2 control flows then merge. One parent has p with a valid state in it, the other has p with an invalid state. What to do, what to do. There's really only one thing we can do with this: issue a compiler error. The rule is, when multiple control paths merge, the pointers in those control paths must all be in the same state. The pointer values don't need to match, just the states. The states must be all valid or all invalid. Furthermore,
destroy all humans.
Damn it, I told you not to do that.
Daisy.
Sorry about that. My D9000 AI bot has been converted to D and has gained a little too much power lately. To relate this to storage allocation, think of our function f as malloc and our function g as free. In fact, we also simplify malloc and free, so they just allocate in integer. Now we can see how live functions solve the memory allocator problem. Note that the memory allocator functions themselves cannot be live because the protections live offer make it impractical to craft a storage allocator. Malloc and free remain system functions that are trusted to behave themselves. You cannot have everything. Visiting once again a previous example from the point of view of storage allocation, this illustrates one type of memory leak detected: allocate and never free. Memory leak number 2 is losing a pointer because its value was overwritten. Double free is easily detected, as the first call to free transfers P's ownership of the allocated memory to free. The second call to free is an error because P's value is now undefined. Similarly, use after free is detected the same way. The value of P is transferred to the free function, and so it is no longer valid and can't be used anymore. A borrowed pointer is not the owner of the memory and therefore cannot be converted to one, so attempting to free a borrowed pointer fails. Note that all these checks are successful without the compiler having any knowledge of what malloc and free actually do. It's just following the @live rules. Moving on to constant pointers. Recall that we can have multiple constant pointers as long as there are no mutable pointers live at the moment. The function Pluto is an example of enforcing this while using non-lexical scoping. The owner P is considered invalid until it is used again, and its use again invalidates all of the constant pointers forward from that point. Calling functions also enforces the rule that constant pointers cannot coexist with mutable pointers. In this example, function bar1 accepts all constant pointers that borrow, so we can pass owner pointer P to them. Function bar2 accepts a mutable pointer and a constant pointer, so passing the same pointer for both parameters results in an error. Remember the ref counting problem from earlier in the presentation and from the DIP 1021 solution? The @live generalizes this from the obvious case in the example to all cases of it, such as hiding the provenance of a pointer through a trail of assignments and function calls and returns. The point of data flow analysis is pointer aliases cannot be tricked. Since the language cannot track global variable usage, reads and writes to global variables are simply not allowed in @live functions. Arguments must come through the front door of the function, meaning through the parameter list. Global variables are code smell regardless and should be avoided in modern code, so this should not be a burden. This presentation has only talked in terms of pointer types. Of course, D has many pointer types, perhaps too many, that are not called pointers but are implemented as pointers under the hood. The @live semantics treat them as pointers. As experience with DIP 1000 showed, this can result in baffling error messages and certainty that the compiler is full of bugs. Regardless of whether the compiler is buggy or not, the way to understanding this is to rewrite the section of code in question to use raw pointers instead of the higher level constructs. An example would be to explicitly pass a pointer rather than rely on an implicit this reference. The error messages and actual problem then tends to come into focus. Unfortunately, using @live successfully will require a sharp awareness of where the pointers lurk in your higher level types, because the compiler knows they're there even if it's not obvious they're there. It isn't going to be easy, which is a big reason why this feature is designed to be used incrementally rather than forcing one to commit to a total program redesign. Emphasizing that all pointers are treated the same, pointers allocated by the GC are treated the same as well. The @live function semantics have no knowledge of the GC. GC pointers do not need at-live semantics to be memory safe. This implies that although GC pointers can be used just fine in at-live functions, they'll lose flexibility, and it may be appropriate to segregate use of GC pointers into other functions. To be used incrementally, at-live functions need to be called by non-at-live functions and to be able to call other non-at-live functions. Unlike at-safe functions being restricted to only calling at-safe or at-trusted functions, at-live functions can call any function, and any function can call at-live functions. The caveat, of course, is that functions that interface with at-live functions need that interface to comply with at-live rules. There is no way for the compiler to check this. It will have to be checked manually. I've saved the worst for last, exception handling. An exception can be thrown by any function that is called, and as it gets wound, all the destructors in scope in the current stack frame need to get executed, along with any finally blocks. Any catch blocks that catch need to have the stack frame for them properly restored with the right values in the right variables. All this complex control flow just tends to shred any useful data flow analysis results. As a pragmatic reaction to this, optimizers tend to just abandon doing data flow analysis optimizations in the face of stack unwinding. Data flow analysis optimizations are, of course, optional with an optimizer. Oddly, most people do not seem to notice this performance deficit is happening. We've heard that exception handling is free unless exceptions are actually happening, but it is completely false. Just the possibility of exceptions being thrown is enough to cost plenty. This puts us in a difficult spot with at-live, which requires data flow analysis to get the pointer states correct. What does at-live do? It just issues a compile time error if at-live functions would need to handle exception unwinding, which means that all functions they call will have to be no-throw. This is part of why I've inaugurated a push to move away from throwing as default behavior to no-throw being the default. You'll like the performance gains anyway from not using exceptions. My forward-looking opinion is that exceptions are obsolete and are going to fade away in modern languages. The at-live prototype implementation has been live, so to speak, in DMD releases for some time and other fine decompilers everywhere, though I did fix a couple problems discovered while working on this presentation that may not have filtered into the released compilers yet. This design for memory safety for allocations fits nicely in with the rest of the D language. It builds on the already successful features of D that enhance memory safety. It's a large step forward in achieving mechanically guaranteed memory safety. Best of all, it does not break any existing code, it can be added incrementally, and it does not require one to throw away all D experience and learn a totally new language. All existing D libraries will still work with this. Give it a try today, come on the D forums, and tell us your experience. We'd love to hear from you.